Good afternoon, ladies and gentlemen. I have never met Jim Wilkinson, unfortunately, but for different reasons than the people before me. Simply, my first meeting in the West was in the summer 1990, and before that, simply I couldn't travel for the meetings. So that's unfortunately I missed that. But I very much feel an honor to be able to give a talk in front of you on this occasion, which is for me also for that reason very, very special.
Zdenek, speak more loudly.
Okay, I'll try. So, well, the title Perfidious condition number maybe sounds intriguing. You may have noticed that the last homework that Margaret gave here of Jim Wilkinson was linked to the PDE. So I just built up on that, okay? And so here's an example of a PDE which is used as a model problem. It's a standard but kind of very realistic thing. It's a Mainz divergence. Here we have function, but it can be a tensor and gradient. And there are prescribed boundary conditions, okay? This was used, for example, in this paper that got some prizes, and it's very, very beautiful. So why I'm showing this? Well, here K is highly discontinuous function, okay? So it has some singularity. In two quadrants is different value, in the other two quadrants is also different values. And now we look at CG, because its discretization is, of course, this is elliptic self-adjoint, discretization positive definite matrix, symmetric. So we use CG. We precondition. We have two preconditioning here, incomplete Cholesky and Laplace operator preconditioning, okay? So we precondition by inverse Laplacian. Okay. And now, for the incomplete Cholesky, we have condition number 16 of the precondition matrix. For the Laplace operator preconditioning, an order of magnitude higher. Now we look at the convergence curve. Something is wrong, because the blue is much slower than the red, while the condition numbers are different, are flipped. So doesn't make a good sense, does it? I am not arguing in this talk about preconditioning this way or the other way, okay? This is not about which preconditioning should be chosen. I'm trying to explain what's going on and why, okay? It's even more puzzling. You know, if you look at this convergence curve, that's clearly something goes on starting from the fifth iteration. We have straight line going down in this Laplace preconditioning, Laplace operator preconditioning, and almost straight line also going down with this incomplete Cholesky preconditioning. Here there is a kind of a little nervousness of this red curve. I'll talk about that at the very end. But otherwise it's very straight, follows the line. So what are these two lines? Okay. What I'm going to show at the end, that essentially we know what these two lines are and what is this point a priori looking at the operator itself. Well, so I mentioned the condition number, and so condition number will be used in some sense in this explanation and don't use it in the other sense. So I will argue how the condition number cannot be used, and then I'll argue how it should be used. Okay? So for that I need to say a few words about closed subspace methods. So what they are, just think about operator equation, G is equal to F in some Hilbert space, can be finite dimensional, infinite dimensional, doesn't matter really. So what we have in the step n, 5th iteration, 10th iteration, whatever, we just approximate the solution, which is the operator inverse with respect to the right-hand side, by the polynomial in the discretized operator with respect to the same right-hand side, okay? Well, and this polynomial is constructed in such a way that it is in some sense, the approximation in some sense optimal, and in the closed subspace methods, so that means that the approximation lives, if I consider the starting initial solution 0, in the closed subspace. That's what it is. And this description, well, many people have contributed to that. Here there are the people who I just mentioned who did the infinite dimensional setting. just for flashing, what I will do, I will use spectral decomposition of that operator, okay? So we all know the standard textbook, so we can identify, say, the description using the Gauss, the integral operator or the Riemann-Stieltjes complex plane or the Riemann-Stieltjes integral, where E here is the kind of a sequence of projectors or projector function. And the same thing, of course, is valid for operators. That means we can extend it to the compact operators, non-compact bounded operators, self-adjoint, and partially also to non-self-adjoint. Without the Riemann-Stieltjes, that cannot be done. And in description of, because we have polynomials, and polynomials optimal in some sense, so what plays here definitely a very important role will be moments. So let's think what is the first moment, okay, of this operator G. And the first moment, just standard textbook, if I plug in the spectral decomposition, is nothing but the Riemann-Stieltjes integral with respect to the distribution function that is defined by this spectral function E, okay? For the matrix it's straightforward, for the operators it's pretty straightforward too. And by the way, this is at the beginning of functional analysis. If you look at this Hilbert paper 1906 about Fredholm operators, so exactly what it's at the very beginning with the thanks to Stieltjes. Well, now back to the CG. So because CG is optimal in such a sense that the discrete operator matches the maximum number of moments of the continuous operator, if I in infinite dimensional space, or the original operator, if I in finite dimensional space, that means that CG and the Gauss quadrature are exactly the same things. They're only put in a different framework. Gauss quadrature works with polynomial approximations, etc., etc. CG works with operators and solves the equation, or matrices and vectors, so if you like. So Gauss quadrature is written here. So we have this distribution function determined by, again, the spectral decomposition of the operator and the corresponding right-hand side. And then we have, here is the Gauss quadrature, here's the error. If you write in terms of the CG, you'll get this equation with the same Gauss quadrature here, and the error in the Gauss quadrature is the same as the error in CG. That has been described in many works, has become basis for the error estimation. Here is very nice survey given in this Congress, International Congress of Mathematicians by Jean Golub, and many other works can be found elsewhere. So now how it is with this condition number? So the condition number just takes a little information, just the edges of the spectrum, doesn't count what is the spectral information inside, and says, well, there's this bound, and CG definitely must satisfy this, which is true. There's nothing wrong with that, okay? The only thing that it doesn't count, what is the distribution inside of the lambda 1 and lambda n? And this is a big problem, because this bound will be reasonable if and only if this distribution is about, say, regular, okay? So if you look at the history, so Rutheshauser as well as Lanzos considered CG very different. They knew about this. They didn't put the formula, but they knew about this link. And they considered something completely different. CG, and because this bound is based on the Chebyshev polynomials. And Daniel, in the work where this appeared for the first time as a formula, just wrote, well, he gives the warning, be careful, okay? So that's what I've said already. So the Chebyshev polynomials, we must be cautious when we replace the optimal CG polynomial by the Chebyshev polynomial and arrive at the estimate. So again, that's what we are going to understand now, okay? So what happens? We'll look at the corresponding distribution functions. What are they? So here, So here is the distribution function for the Laplace preconditioning, and here's the distribution function for incomplete Cholesky preconditioning, this black one. Don't see any big difference, but there is a big difference. In the top part, what do we have? We have outliers to the left. 1, 2, 3, 4, okay, outliers. And then on the right, we have one outlier. What happens? CG, when it looks at this problem, so in the first few iterations, it localizes these eigenvalues. This outlier to the right and this to the left. These outliers to the left, if they are localized, they doesn't need to be approximated very well. There's a very nice theory by van der Forst, van der Sluis, by the way. And it can be shown that here rounding errors doesn't matter to the left. They can be localized, just one Ritz value to one eigenvalue, just rough approximation. And from that point, CG just behaves like they are not present at all. On the right, it is not true, because CG localizes very quickly, but after a while, it put another Ritz copy, another Ritz copy, another Ritz copy. It behaves like here it would be a cluster of eigenvalues, okay, in finite precision arithmetic. But because our convergence is so fast, it doesn't count. Simply no second Ritz value appears, okay. Only at the very end, you can see there was some nervousness starting to be. So that's an example. If you would continue, that we will see that it will stagnate for one iteration. And then it will continue with the same speed down, okay? Because of rounding errors. But they don't show up. So essentially, the convergence of CG for this Laplace preconditioning is driven only by this part of the spectrum. That's why it is so fast. And it must start at the 5th iteration, because we need just 1, 2, 3, 4, 5 to eliminate those. Here the situation is very different, because we have many eigenvalues here, so nothing can happen on the right side. And on the left side, we can eliminate only this 1, 2. That's it. And no possible acceleration, because the distribution in between is kind of so, I would say, regular that no acceleration can happen. Okay, so that's the explanation when I know the spectrum. But we do know the spectrum. And there's the theorem in this paper, which is now going to appear in SAM Journal Numerical Analysis. I think it's very new, and it is a collaboration with two colleagues from Norway and my PhD student Tomáš Gergelic. What this theorem says: looking just at this function k, and we take any discretization you like. There is no restriction which finite elements you use. Here it is done for Laplace Lagrange elements, and you just use Galerkin discretization. Okay, so it is proved that there is one-to-one correspondence between the values of this function k at the nodes and the eigenvalues. So essentially, we have pairing. So if you look at the values of the k at the nodes without doing any computation, just computing these values at the nodes of the discretization. And the discretization is fine enough. We know the spectrum, the whole spectrum. If we have an area where the k is constant, we know eigenvalues exactly, including a multiplicity. Okay? That's exactly what happened in this example. The proof is, my biased opinion, very interesting, because the first part of the proof is based on the perturbation argument, very much in line of Jim Wilkinson, that just shows little local perturbations will tell us something. And then this something is actually a base for using the Hall's marriage theorem from bipartite graphs that shows the pairing. Okay, that's it. So it's combining many fields. Okay. How it is with the clusters of eigenvalues? I've already mentioned this. So if you have clusters of some cluster of eigenvalues, which is very far to the right from the spectrum, we cannot replace it just by one eigenvalue. It can really destroy the convergence of the CG, even if it is only one cluster. So we just cannot say in general that if you have T clusters, that means good approximation in T steps. Okay, the conclusion. Well, curve subsegments adapt to the problem, and that's why we have to really consider many things if we like to solve challenging problems and we'd like to see what will happen. So it's a very interdisciplinary issue, and this cannot be avoided. And I like to end up with the quote Jim Wilkinson. Well, yes, the condition number is absolutely essential thing. That's how he defines that, and that's nothing to add to that. Well, it's a nice quote from Forsyth. He says, well, you know, this conditioning is really important, but it's a whole group of ideas, but we must be a little bit cautious. And he said, well, that's related to preconditioning. He didn't elaborate on that, but exactly explains or somehow indicate the trouble that we are trying to explain. Well, we don't argue in the book with Joseph Malek about preconditioned CG in infinite dimensional spaces and discretization against condition number. Not at all, because we use this condition number here. The slopes were given by the condition number for the reduced spectrum. But many other things were included, like the rounding error analysis, numerical stability, etc., in order to use this condition number. Finally, the last thing perhaps I will use from Wallace, founder of London Mathematical Society, that I think explained what we are trying to do. And thank you very much for your attention. I'd like just to show you, if I don't know what to do, so I'm asking my collaborator on the next slide, but she is not on the slide mentioned. So.
So can we turn it around and say, what do we have to do to the PDE rather than the linear system to precondition,
Yes.
in quote, it in such a way that the discretization method gives us a good system to solve?
I didn't have time to talk about this, but that's the purpose of this work. Actually, this is not the end of the story. And this is not the precondition that we advocate. The preconditioning must use this information that we know the spectrum and to build up the preconditioning from the spectrum. So that's the second step. The work is going on, and some other two papers are on working papers, are not yet submitted, or some they will take some time. But we go in that direction. Yes, that's exactly what it is.
Anything else?
Comment to make. Go ahead. So half the people in the room know, but maybe the other half don't know, that this whole business of practical computation with iterative methods related to CG was started by John Reed, sitting right there in 1971. So it's fantastic to be in the room with you, listening to this talk after so many decades of progress.
That, if I make that, it's very true, and I think the mathematical community in particular should be thankful to you, because engineers use CG, but mathematicians abandoned it. And your paper, yes, that is true. And your paper just revived the whole attention, said, hey, we should just use it, you know.
I didn't do very much. I just tried it.
Yeah, well, no, exactly. But then you articulated it in the way that the people understood and started to be interested.
Thank you, Nick.